I'm Dustin. Like he said, I'm a developer advocate at Google. So I focus on supporting the Python community at Google and talking about things that are good for Pythonistas at Google at conferences like this. I'm not going to talk about any real Googly stuff today. I'm also the chair for PyTexas. It's not too far away, and it's not too long from now. If you're interested in coming to Austin, Texas, we'll be there May 16th and 17th. And like you said, I work on the Python package index and some of the other packaging infrastructure and tools, but also I'm not talking about that today. All right, so pop quiz. Is Python dynamically or statically typed? Who thinks it is dynamically typed? Raise your hands. Who's like, wait, he's going to talk about static typing in Python. It's probably statically typed. Raise your hands. Who thinks this is a trick question? Yeah, OK. So the answer is Python is dynamically typed, but you can optionally statically type it. This means that Python can be basically as statically typed as you want it to be. And that answer might not make a lot of sense to you, and that's OK. That's why I'm giving this talk. So the steps to understand what that answer means, we're going to talk about a couple things. We're going to talk about types in Python, type systems in general, like across other languages as well. We're going to talk about dynamic typing in Python, and then we'll talk about static typing in Python. And then once we understand all those things, we'll talk about how to use static typing in Python, because it turns out, yes, you can do static typing in Python, when you should do it, and when you shouldn't do static typing. So let's talk about types, and let's specifically talk about type. Type is a built-in in Python. So I can say type of 42, and it will tell me the type of that is an int, right? Makes sense. We've probably done that before. Same thing for floats, strs, and lists, right? This should all be pretty familiar. And yeah, so yeah, you can be like, yeah, I recognize all these. I use these built-ins from time to time. Maybe I can assign a variable to A, and then I can use these things like float, str, list to change one type of variable to another, right? So you could do like turn the integer into a float. You turn the float into a string. You turn the string into an ugly, ugly list. Who's had something like this show up in there? Yeah, so this happens. That's a weird bug, right? That's a type error. You were expecting something like a list, and you got a string instead, and you got like this really long list as all the characters of your string spelled out. So that means if you've had that problem, you're in the right place. And I'm going to talk to you about how you can fix those kind of bugs. So it sort of seemed to you that maybe these types are available to us. But these are actually just classes that correspond to these built-ins, right? So when I say that type 42 is an int, I'm really actually just doing like class matching. Int is just another class, like a class that we define, like any other class you've ever written. So I can do like, is instance 42 int? And it will say true. Like, it is an instance of the int class. There are also other types in Python that don't correspond to things like int and float, these built-ins. So for example, the type of none is none type. I'm sure you've seen it before, but none type, you can't type none type in a Python REPL and get a type. It's not there. Same is true for function. You do the type of a function, you get class function. But we don't say, like, we don't use the function word when we write Python code. We say def, function, name, whatever, whatever. And there's also like ellipsis. There's the ellipsis type for whatever ellipses are for. So there's other types as well. So you can import the types module, and this is in basically any version of Python, and you get a whole bunch of stuff. And so many of these types live in the types module. And these classes can actually be used to instantiate these objects. For example, a function, there's a function type in the middle there. But we don't do that. And we don't do that for a good reason. It's because it can get really huge and gnarly and messy, all the arguments that go into instantiating these classes. Instead, we just write functions the normal way. So dynamic typing in Python, when we say that Python is a dynamically typed language, that means that variables can be any of these types at all, right? And they can change. A variable can be instantiated as one, and it can become something else. So like, I can import random, and I can do random.choice of multiple types of objects. And what is the type of A here, right? It actually could be like any of these things. It's totally non-deterministic. So the type of A is flexible, and we can change it as we want. That's dynamic typing. Dynamic typing also means that the arguments and return values of a function, just like a variable, can change, and they can be different. So they can be any type at all, and it can, we don't actually know what the return type of function can be. It can change depending on the behavior of the function. So if I define a function like this, frobnicate, just a made-up function, when we write a function like this, how do we know what types this function is expecting, right? So if you saw this function, and you didn't know what it does, because you don't know what frobnicate means, What would you expect the argument and return types to be here? Any guesses? What the types of the integer? Okay, sure. So yeah, if you created this function, you could call it with integers, and you would get the sum of those integers, right? Maybe that's what it does. You could also pass it strings. That would totally work just fine. It would concatenate the strings. But what you couldn't do is mix those types, right? You couldn't pass it two integers and a string, because that would just create a type error. You can't combine strings and integers like that. All right, so this is really confusing. How should we fix this? So one thing we could do, we could write really long doc strings. They look like this. Sometimes we do this. Who does this? I don't do this. Are they paying you guys enough to do this? Because that's a lot of work to get those exactly right. And the thing is, after you write those doc strings, it doesn't make any guarantees about whether your function is actually going to get called with those types. It's just sort of a little bit of extra knowledge to the people that are looking at your code. We could do this. We could assert on all of the argument values and on the return type. We definitely don't do that, though. I've never actually seen Python code that isn't a test that does that, right? That's a mess. Don't do that. Instead, what we do is something called duck typing. So basically, if it walks like a duck and it quacks like a duck, it is probably a duck. We just sort of like manipulate and do things to objects in Python, and if they do what we expect them to do, that's what they are. So here's some examples. And each of these you can kind of guess what bar is based on what's being done with it, right? But like in the first one here, bar is probably like a list or a string maybe. In the second one, bar is probably an integer or a float, something we can compare with 0. And the last one is kind of ambiguous, right? Like that could be a function, it could be a class. It's not really clear just looking at it what it is. Usually we would capitalize the F if it was a class. But it could be anything, and also the return value from it could be anything at all, right? We have no idea what it's going to give us when we call it. So this is where static typing comes in. Basically, static typing means that a variable or a function is defined to only return certain types. And static typing exists in a lot of other languages as well, right? So here's some examples of that same function in those other languages. Does anyone know what language this is? It's C? Yeah, that's C. How about this one? Java, yeah, it's kind of obvious. Anyone know this one? Rust, yeah. So Rust has like really fine-grained control of the integer type. That's an unsigned 8-bit integer. You can have all sorts of different types. How about this one? Anyone know this one? Yeah, that's TypeScript. It's a dead giveaway because in JavaScript, there's only one type of number. It's a number. There's no integers, there's no floats. So you can sort of put languages into two categories, right? Dynamically typed and statically typed. And you can sort of think, if you've programmed in any of these languages, you can remember, like, yeah, in Java, I had to say public static void int whenever I created a function that returned an integer. I'm going to put a little asterisk here next to Python. We're going to talk about why, obviously. And also, I want to point out that Ruby is technically going to also get optional type checking, but it won't happen until the end of next year. So for now, it's still a dynamic language. So yeah, Python is dynamically typed, like I said before, but it's optionally can be statically typed. And this wasn't always true. When Python was first created, it was definitely solidly in the camp of a dynamically typed language. And really, the story of Python becoming a optionally statically typed language is also the story of the introduction of statically typed code at Dropbox. So Dropbox has millions of lines of Python code. And they basically decided at one point, hey, Python is getting kind of messy. We kind of need static typing. And I'll talk about why in a second. But there were some other things leading up to it before Dropbox started adding static code. By the way, they just published this blog post. I'll include a link later, like 2 days ago, actually. And it's a great story of how they adopted static typing in Python. So let's go back a little bit. In 2006, Python 3 was about to come out. And we had a PEP 3107. And this introduced function annotations in Python. And you might not really have seen this too much. It wasn't really super useful for a lot of things, maybe except for typing. So it allowed us to take a function like this and add any metadata that we wanted to annotate the arguments and the return value of that function. So this would have zero effect on the execution of that function, the behavior of that function, the runtime of that function. But literally, you could do anything you want, right? Like here, I am adding 5 and 6. I'm taking the max of 2 and 9. And what happens is, after that function is evaluated, I can get the Dunder Annotations attribute, and that has all of those things after they've been evaluated. So anything that's compiling this function has access to all these things, and it can do some interesting stuff with it. And that PEP included a huge list of things that could be done with function annotations, right? There are a lot of options. They all kind of boil down to something that kind of looked like typing, and then like maybe documentation, which isn't super useful because we also have comments. So this allows us to write a function that would look like this, where I specify the type for each of these arguments and also the return type. But what it doesn't do is give us a way to evaluate whether this function is being correctly used, right? Like again, nothing is actually going to check whether these values are correct and whether it's actually being used correctly. So around the same time, Yuka Lengpaso was working on his PhD research at the University of Cambridge. And his PhD thesis was basically about the unification of statically typed and dynamically typed languages. This is still back when Python was totally dynamically typed, and he was kind of looking at Python as an example. What he wanted to look at was ways to use the same language for everything from a really tiny script all the way to sprawling multi-line code bases and have static typing be optional. And this would allow for gradual growth. It means that you could take something that was dynamically typed and slowly turn it into something that was statically typed. You don't have to do it all at once, which sounds really nice. So he published his thesis in 2011, and the TLDR is this. Basically, he determined that adding a static type system to a dynamic language is basically totally invasive and would be a huge dramatic change, require changing basically everything in the ecosystem and not really advisable. However, he found that you could create an optional pluggable type system that doesn't actually affect the semantics of a program and wouldn't actually require changing a bunch of existing code and tools to support it, or really breaking compatibility with the language. So this sounds pretty nice. So what he did was in 2013, he gave a talk at PyCon, and he introduced something called MyPy. And MyPy at the time was maybe, if you've heard of MyPy before, it's not what you think it is. He introduced MyPy as an experimental variant of Python, which would support writing programs that seamlessly mix dynamic and static typing. So basically, in his research, he couldn't use any of the existing languages to determine how to do this. And since it was just research, what he did was he created his own language. I forget what it was called, Allure, I think is what it was called. And this language could be compiled to Python, and that language also supports static typing. And it looked like this. So it kind of actually looks a little bit like Python, but it would let us do function annotation and variable annotation and all those other things. So the issue was that even with the function annotations that I just talked about, Python couldn't support everything that was necessary to be statically typed itself. And so what happened was he gave this talk at PyCon. He presented it, and then he talked to Guido about it afterwards. And Guido was like, hey, don't keep working on this Python variant. Let's just make this work with regular Python, which I think was a good idea. And at this time, the other thing to note is that MyPy was this variant, but it also included this type checker that you could run on the variant to determine if it was correct, if the typing was correct. And that type checker is actually what we'll see becomes MyPy. So they did some collaboration, and Guido published PEP 483. This is Guido's theory of type hints. It's basically some really high-level ideas about how typing should work in Python. So one thing really important to Guido that he got from Yuka's research, optional typing, right? And I think this is sort of a lesson that we learned from the Python 2 to 3 migration. We want to make this optional. We don't want to make this invasive. We want to make this easy for people to adopt. So basically, an annotated function or an annotated variable should be and behave exactly the same way as one that was not annotated. You shouldn't actually notice the difference. The other was gradual typing, right? You shouldn't have to type your entire code base all at once. If you have 5 million lines of Python code, that's actually impossible. So you should be able to type some of your code, leave some of your other code untyped, and have them run together and have it not cause problems. And also, if you want to check the code, be able to check only certain parts of it. Another was variable annotations. So we had function annotations already. We needed a way to annotate variables. And the PEP talks a little bit about how we could do this. So if I had a function like this, I have the return type bizbaz in the middle there. We could just add comments, basically, is what Guido said. We could add a type comment that says it's int, and our type checker can infer from the comments what the type of that variable should be. So this is sort of like a way to sidestep around actually having to change the syntax of the language to support this. And the nice thing about type comments is that even though we got function annotations in Python 3, type comments mean that we could go back in time to Python 2 and still do static typing. So even because, even though stuck in time, like they deserve function annotations and static typing as well. So you could take a Python 3 typed function like this, and you could type it in Python 2 as well by adding a type comment. Thanks. This PEP also introduced some special type constructs, which didn't exist before, which were really important to being able to do static typing. So we had existing types like integer, float, str, but it also introduced some new types. And these came in a module called the typing module. So things like any. Any is like a wildcard for types. Any type will match any. Union is a combination of multiple types. So it'd be a variable that could be one or more different types. Optional would be the alias between one type and none. And there's also tuple and callable, which would represent a function. So this would allow us to write a function like this now. We could use union to say that, OK, for Omnicate, we'll take an integer, and then the third argument could be an integer or a float. And thus, the return type, if we're adding possible floats to integers, that should also be a union of an integer and a float. And this would be typed, checked as valid, right? And we would be able to verify that every time that we call for Omnicate, it has an integer, and then something that looks like an integer or a float. The other thing it defines is container types. So container types are things like lists and dictionaries that contain other objects. So in the PEP, it says, all right, well, we want to be able to say, like, I'm going to create a list, and the list is only going to be integers. So it creates a way to create new types from base types, like a list, to say, OK, like I can add integers to my list, but I can't add strings. If I had a dictionary that had a key of a string, value of an integer, I can't do the opposite of that. It adds generic types for when a class and function behaves in a generic manner. So this would be like just the general iterable class, for example. So if we just want something that supports the iter function, that could be a whole class of different things. If we want to just say, all right, this is an iterable that has tasks inside it, we could create a new iterable type. And I said here, like task, I'm using as a type here, but you can see it's also defined as a class. The other thing that this PEP did was it gave us the relationship between classes and types. Basically defines what a type is, how subtypes relate to it, and the difference between what a class is and what a type is. Because like I said before, when I say type of 42, we're actually getting a class here. A class is just a type. So we can create new classes, and these are basically the same thing as a type of that instance. So we can use type to determine what the class is here. And yeah, actually, I bet most people didn't know this. You can instantiate an int, right? An int is just a class. Int open close paren will give you 0, and the class of int is just, or the type of that integer is just an int. And then we can also do custom classes. So a custom class, obviously, is still a class, but it can also be a type. So we can use this as a type elsewhere. And then the other thing to note is that these special constructs that I introduced before, they can't actually be instantiated, right? It doesn't make sense to instantiate the union of a string and int. It doesn't. What is that even? The one last thing that this PEP introduced was the ability to basically alias types. So if we wanted to be a little bit more like JavaScript, we could alias number to the union of all of our number types, and yeah, it'd just be a little more confusing. This is another PEP, PEP 484. So this basically took everything that was defined in the theory of types in Python and standardizes it. Standardizes everything in PEP 483, and essentially standardizes MyPy's behavior at this point. It introduces the typing module to Python, includes a lot of details about edge cases, specific use cases, and basically just gives us all the building blocks and tools we need to have a type system. So that was released in Python. PEP 484 support was in Python 3.5, which was released in 2015. Not long after that, we got PEP 526. This gave us a true syntax support for variable annotations. So we didn't have to keep using comments like this. If we were instantiating a list, instead of the comment, we could just do this, sort of like what we do in the arguments. One problem with the comment annotation, it was awkward to instantiate a variable that didn't have a value yet. So in the second example, that just becomes something like this, and you don't have to give it a value at that point. And like the same thing for these things, right? A class variable is of a dictionary of strings and integers. So PEP 526 support came in Python 3.6, which is in 2017. And at this point, we had almost pretty much everything to do static typing in Python. The last thing we needed was a type checker, right? What use is writing all these annotations in your code if there's nothing that's going to check it? So it's the last piece of the puzzle. And basically, there's two kind of types of type checkers. They're also static and dynamic. Static means that they're not actually going to execute your code. They're going to look at it at rest and infer from it how it is written, what the types are. Dynamic is going to actually run with you at runtime and watch what your types are as you go. So by this point, MyPy had transitioned from this Python variant that was kind of weird into just a type checker, right? And that was available on PyPI, and you could install it, and you can install it now. And the way it works is you install it. You have a little file that has some Python code in it that's annotated, and maybe it's not being done correctly. So if you run MyPy on that file, it will throw a bunch of errors. And it'll say, all right, your arguments, They're supposed to be strings, but or supposed to be integers, but they're strings instead. So there are a bunch of other type checkers besides MyPy at this point. So basically all the kind of big Python shops have their own type checkers. They all support PEP5 for PEP484, which is the standardization PEP. There are others that don't support that specification exactly, but these are the ones that are probably most in use. MyPy is from, at this point, it's mostly from Dropbox and supported by Dropbox. PyType comes from Google. Pyr is from Facebook. Pywrite's from Microsoft. And there are other, those are all static ones. There are dynamic ones as well. They don't come from the big companies because a dynamic type checker, thanks, is going to add a little bit of overhead to the actual running of your function. So they aren't maybe used as much in production. So disclaimer, like I said, I work at Google, so I actually am somewhat partial to PyType. It's also available on PyPI, and the inevitable question whenever you talk to someone about multiple type checkers is like, okay, what's the difference? Like they both support PEP484. Why would I use one or the other? Like is one a little bit faster, save me some time? And so there are actually some differences between the two, and they basically, the differences are things that aren't specified in PEP484. So for MyPy and PyType, which are probably the most widely used ones, the differences are what I'll call cross-function inference and runtime lenience. So the first example is, if I have this code, it's totally untyped. The first function returns a string, second function calls that function and then tries to add an integer to it. If I run this, it's gonna fail, right? I'll get a type error. You can't add strings and integers together. If I run this through MyPy, sorry if that's a little small, MyPy does nothing. MyPy's like, we didn't type any of that code, I don't know what it is, so it's between multiple functions, I can't keep track of this. If you run it through PyType, PyType will blow up and say, hey, like I know this is going to be a runtime error. I can infer that from the way that you're calling these functions. You probably want to fix that. And that's actually pretty handy because when you're migrating code from dynamically to statically typed, a lot of your code is still going to be, these other functions that you're calling, they're not going to be typed. They might be in a third-party module, might be elsewhere in your code base, you're not ready to type it yet. So this functionality is actually quite nice, I think, in PyType. Another example is this example. So here's some more untyped code, right? We're creating a list. We're trying to append an integer to it. And that should be fine, right? This is totally valid Python. We create a list that has a string in it, append an integer, and then we cast them all to strings and return that value. So if I run that, that works, like PyColorado 2019. If I run that with PyType, it says no errors found, right? Anything that is that would work when you run the function, it's not going to raise an error on because it's not actually going to cause problems. MyPy, for example, however, will actually say, hey, I noticed that you had this list and you put some strings in it, and now you're trying to put integers in it. Like, I think that might be a problem. It's a little more stricter about those things. Okay, so you might say, well, why though? Like, why should I use static typing after all of this? So first I'm gonna say why you shouldn't use static typing. And the answer is basically never. There are some times that you might not want it. One example that I want to point out, static typing is not a replacement for unit tests. So there's actually like kind of a school of thought here that, because unit tests are actually sometimes, they end up kind of just being like a bad type system. This tweet says, well, basically type checking catches all these bugs that existed even when unit tests existed, and unit tests are kind of acting like bad type system. However, it's kind of just a bad idea to get rid of your unit tests and replace them with static typing. Like you actually kind of probably need both. You need unit tests and you need static typing. When should you use static typing? Basically, use it as much as possible. Use it liberally. You should use static typing if you're at millions of lines of Python code scale. Definitely, if you're at this point, you probably are like writing your own static type checker or using one of the ones already. But that's the point where it's kind of the sweet spot. Yuka said in this blog post that he recently published, at Dropbox's scale and at Facebook, Google scale, basically these companies invested a lot of money in the work that they've done with static type systems because the lack of static typing is a huge liability for Python at this scale, right? It makes the code needlessly hard to understand. It's hard to pick up. It's hard to look at code and understand what it's doing when it doesn't have types. So basically, this is the graph that you should have in your mind. As your lines of code increase, your desire to add type annotations is definitely going to go up, and it will start to go up very quickly. And the ease of doing it will go down. And there's a sweet spot here, right? So you're probably like here, and maybe your company's about to get like Dropbox size, and you're going to have millions of lines of code. That's where you should migrate. That's where you should start adding type annotations. That's probably where you're actually going to do it. But that's OK. You'll still be able to do it. I mean, Dropbox is able to do it. They've ported millions of lines of code at this point. You should also use static typing. Casey, you want that one? You should also use static typing just when your code is going to be confusing. Like, let's be honest, we're all writing confusing code. I've written confusing code. Annotations are basically, and this is not my quote, annotations are basically machine-verified documentation, right? Your machine will verify the documentation that you've done by adding type annotations. If you feel like you need to document what the input and output of a function is going to be, you probably should add static typing to it. You should also use static typing when your code is fit for public consumption. So if it's going to be a module on PyPI or a library that's shared amongst multiple services in your team, adding type annotations is going to let developers know how to use the APIs that you're distributing with your module. It also is going to help IDEs like PyCharm figure out where and how to use these modules as well, do autocompletion, that kind of thing. And also, if your users are already using static typing, they're going to really love that your third-party code is statically typed as well. Another time to use static typing is before migrating or refactoring. Static typing is going to be really helpful if you're doing a huge migration, right? Because you're going to know immediately if you statically type all of your functions, and then you go and do your refactor, your migration from one Python version to another, it'll tell you when they break. So it's really helpful there. You should also use static typing if you just want to experiment with static typing, right? It doesn't hurt, and it's not going to slow you down. It's just kind of interesting to experiment with, and you should give it a try. And also, you should use static typing if you're just cold. Gary Bernhardt says, static typings are a warm blanket that I have missed so much. So I guess they also make you warmer. By the way, Gary also has like the best background on his Twitter right now for this talk. Gary was stung to death by type errors. Gary's awesome. All right, so here's how to use Python, static typing in Python in 5 easy steps. So first, migrate to Python greater than equal to 3.6. You can do type comments in Python 2.7, but let's be honest, you should migrate anyway. You should install type checker locally. I don't care which one. Just install one of them. You can install multiple ones if you want. I don't care. And then you can start optionally typing your code base. Like, pick your hairiest file or your hardest function, or like pick the easiest one. That'll probably be the easiest to do. And you don't have to do it all at once. Remember, it's gradual for a reason. You don't have to invest all this work into statically typing your entire code base. Pick a critical area and then just start there. 4, run a type checker with your linting. Just do it at the same time. It doesn't need to happen at runtime. Just do it when you lint your code. Do it when you run black. Everyone's doing black, right? And finally, then convince all your coworkers to join you in static typing. And if you need help convincing them, just tell them to come watch this YouTube video. All right, thanks everybody.